Welcome to Lecture 14b, entitled Double Integrals in Polar Coordinates. And we're just going to go through again some examples here. Materials covered in section 16.3 of the text. Objectives are to work out some example problems in computing double integrals in polar coordinates. And this type of problem we're dealing with here will be a little bit more complicated. The concepts and visualization skills are similar to what we've just done in the previous lecture. Integration bounds for radius r and angle theta, visualization of bounding surface in polar coordinates, and the differential area in polar coordinates. As usual, the second slide is just a summary of the slides to follow, so I'll just skip over this slide. All right, so the example problem 1, the problem statement, write an iterated integral for a double integral over region R of f as a function of r and theta dA for the following regions in the xy plane. So part A of the problem is to the region outside the circle r equals 2 with radius centered at 0, 0, that is the origin, and also inside the circle r equals 4 cos theta, which is really a circle with radius r equals 2 centered at 2, 0. And we'll prove that shortly. Part B would be to look at the region inside the circles of part A, which is more or less the intersection set of the two circles. So we're going to use polar coordinates to solve the problem, which mean the transformation equations are x equals r cos theta, y equals r sine theta. So the first thing we wanted to do was to prove that r equals 4 cos theta for the circle of radius 2 centered at 2, 0. So we start by looking at the problem in Cartesian coordinates. We know that a circle of radius 2 centered at 2, 0 is defined by this equation here. So this is an offset of the x, right, plus y squared. This is the radius squared. So this would be the equation of the offset circle. So now we're going to substitute in for x and y using polar coordinates. And so this, if you square this, add to the square of this. After simplification, you get r squared minus 4r cos theta plus 4. These 4's will cancel. And then you can factor out a common r, and you end up with this is equal to 0. This is basically just a quadratic, but a simple quadratic. So the only feasible solution is when this argument 0, which is equivalent to saying that r equals 4 cosine theta. So we basically know that that r basically, when you trace it out, will basically be tracing out the periphery of the off-centered circle. So let's do the solution to part A. First of all, let's look at the picture. And so the picture is shown here. Here's the offset circle. And we're interested in this region here. All right. So in this region, we basically would have r being pointing outwards in a radial direction. And so you would have this as one continuous contour, would be the outer line, and this red portion here would be the inner line. And so the outer integral would be between two angles. And so how do we know what those angles are? Well, it would be basically a line that goes through the intersection point of these two circles here and the two circles here. So this is effectively the integration we're performing. H of theta will be 4 cos theta, which is basically traversing the outer circle, and g theta equals 2 is basically traversing the inner circle. So the angles alpha and beta, which one is here and the other one will be here, are determined by the intersection points of h theta and g theta. So all we're doing is equating those two, which is what I've done here. Simplifying gives cos theta equals 1/2. And there are two possible solutions. One is at theta equals pi over 3, and the other one at theta equals minus pi over 3. So that means the lesser of the two, which is minus pi over 3, will be alpha, which is the lower bound on angle, and pi over 3 will be the upper bound, which is beta. So we can substitute this into the integral, and so this integral is more or less ready for computation. All right, this is just an interactive version of the problem that we just sketched out. So if you're interested, you can look at it and perhaps get some more insight. So the second part of the problem is part B, and here we're interested in the intersection set, which is the region where the two circles basically share a common region, which is here. All right, so now we have a problem because the integral isn't as straightforward, and the reason being that if you were to look at basically the radius here, where you're trying to trace out essentially the exterior contour here. Well, it's fine until you get to here, and then you have to go from this curve to this curve, which means the curve is not continuously differentiable. And we've seen before when you have such a problem, then you have to basically break things up into regions. Not only is there a problem here, but there's a problem down here. So going along the curve to this point, so this is the line that passes through the point. So that's that little barred region that you see here. That will be one region. We'll call that R3. Going from here to here, we're going along one smooth contour. So that would be region 2. And then from here to here, this little segment you see here would be the third region. So going backwards, starting from here and going around, you would have first this region, which is R1, then this region, which is R2, and this region is R3. So we need an integral for this region, and this region. And so we basically have broken it out into 3 separate regions. So we have alpha, which is the low end, alpha 1, region 1, and then region 2 and region 3. So we need to compute what all these values are in terms of bounds, and then the problem has been solved. So we already had solved the intersection problems in the previous problem. So we know this angle's pi over 3, and we know this angle is minus pi over 3. The question now would be, what is alpha and what is beta? Well, alpha basically would be, if you bring this line, as this traverses down right to here, then that would be a line that would be pointing straight down, and so this angle would have to be minus pi over 2. All right, so that's basically what you see here, theta is minus pi over 2. This one's easy, minus pi 3 to pi over 3, and then once you come down through to here, you're looking at this case, now theta has to be pi over 2. So we basically now have defined what the angles here would be, here and here. As far as the inner bounds, which are radius, when we're looking at this portion here of the curve, then we're looking at the portion of 4r cos theta. When we're going basically from here to here, then we're dealing with basically r equals 2. And when we're going from here to here, again, we're dealing with the r equals 4 cos theta. So putting everything together, we can write things out in the form shown here. So this is the outer bound. This is at the bottom, the 4 cos theta. And g1 theta basically is 0. All right. So basically you start from 0 and you extend out until you hit that outer curve, which is the off-centered circle. And we started at angle minus pi by 2 until we got to the intersection point, which is the angle of pi minus pi over 3. So basically there's the final form for region 1. For region 2, we're basically on the circle. So h2 theta is 2. G2 is 0. Basically you just collapse the value to a single point at the origin, and you're going from minus pi over 3 to pi over 3. So now that you have this information, you can put together the integral for region 2. And lastly, basically, we're going from pi by 3 to pi over 2. We're again following the off-centered circle, so that's 4 cos theta. And of course, the radial collapses to 0 so that you can sweep out the whole thing. So then this combined basically gives us the bounds for the third integral. And so you just need to sum these 3 together and you get the final answer. All right, there's an interactive demonstration of the regions of integration for part D, so feel free to explore it if you wish. And the last little problem I want to deal with is something which is called a lemnoscape. And so the problem statement is to sketch the following region R and then express integral of grd theta dA over region R as an iterated integral over R in polar coordinates. So they just want you to set up the integral, not to actually solve it, since g of r theta is not a given. So the region inside the lobe of the lemniscate, r squared equals 2 sine theta. So we need to graph that. So I made a note at the bottom. If you wanted to graph this, you can basically just sort of create a position vector, which is just x of y. And x, basically, because we're dealing with polar coordinates, would be r cos theta, r sine theta. And r is already going to be defined. We can go up here. If you take the square root, this becomes 2 sine 2 theta, so it's a square root. And so if you were to graph this as a function of theta, right, over the full range of theta, then you'd be actually sketching out this region that you see here. So theta equals 0. means that it's a line that's out straight. And so if you were to plug in the values here, you'd clearly get a value of xy00, which would be right at the origin. And clearly at some angle, looks like 45 degrees, right? Then this basically would be sine of 90, right? This would be sine of 90. And this would be basically a value of sine of 45. So that would basically give you the x component and the y component. The cosine would also basically be the same as the sine theta, it's 1/4. So that's why this becomes a straight line. This is the point where it reaches its maximum value out. And then this position vector gets smaller and smaller as you come back to here. All right, so you start at theta equals 0, and you come right to the back at the end when you get to theta equals pi over 2. So the range here would be from 0 to pi over 2 as you make one full traverse of the contour. The region R, well, we know what R squared is, and we know that over the range of theta of interest, that's theta is going from 0 to pi over 2, sine remains positive, sine 2 theta remains positive, which means we can take the square root. So 0 is less than or equal to R is less than or equal to the square root of 2 sine 2 theta. This will be basically the range on R, and this will be the range on theta. And so you can take this information and immediately transfer it to the bounds on the double integral. This, of course, will be the Jacobian times dr d theta. And so this integral is ready to go. We just need to know what g of r theta is. All right, so the last slide here then is the average value over planar polar region. How do you do averages? Well, in this case, basically, we take the function of interest, integrate over the area. In this case, it'll be r dr d theta. That's the differential area. And you divide by the area of the region. All right, and so that would just be taking the f out. It would be just r dr d theta. So let's basically take an example. Find the average value of the y-coordinate of the points in the semicircular disk of radius a given by this. So this is more or less the region over which integration will take place. And you're basically given that we're going to be looking at f of r theta as being y. All right, but we're going to basically have to convert y into polar coordinates, and we know what the transformation y equals r sine theta. And so first of all, if you compute the area, this would just be taking the region, transforming it to the upper and lower bounds, r dr d theta. This just becomes pi a squared divided by 2. All right, so if we're going to compute the average, then it would be the area, this integral. So this y basic, the value of y now is being replaced by r sine theta. So there it is. There's dA, r dr d theta. Divide by the area, which is basically going to be the term that we saw here. So this would just be pi a squared over 2, or the 2 comes on top. And so you're just integrating this. All right, so first with respect to r, we integrate, holding theta constant. And having done that, then we integrate with respect to theta, and we end up with a final answer of 4a over 3 pi. All right, so that concludes lecture 14b. Thank you for listening.